Good morning, ladies and gentlemen, and we're going to talk today about nuclear equations. This is the second part of the notes from chapter 16 about nuclear reactions. So we're going to go through this, and then we got a little worksheet for you to work on after that. What we're going to have to do is make the law of conservation of mass be true in these nuclear reactions. We talked last time about the different kinds of radiation, the alpha, the beta, the gamma, and the positron. So what we're going to have today are all these nuclear emissions. You can see these nuclear emissions. These are things that are going to be given off by things, or they might be added to a reaction on the left-hand side. So in the first three, this is a alpha particle emitted along with a new particle, beta particle here, positron here, and if you'll notice this one, it's going to be, we're going to have an electron bomb this iron in this point. So the thing that has to add up in these equations are the top number has to add up and the bottom numbers have to add up. So here, if you'll look, 235 on the top equals 4 plus 231. If you'll look on the bottom, 92 equals 90 plus 2. Here, this is hard sometimes for people to add. 38 and negative 1 add up to 37, and 87 equals 0 plus 87. Positron, 18 plus 1 equals 19, and 0 plus 38 equals 38. Here, 55 and 0. Here, 26 take away 1 would equal 25. So the tops and the bottoms, that's all you got to remember. This is not difficult if you just remember that the tops and the bottoms must be the same. So nuclear charge cannot be created or destroyed. The total nuclear charge at the beginning must equal what's left afterwards. So that's the bottom numbers now, and those add up as well. So now if we do some alpha particle examples, this is going to be pretty easy. We're just going to do exactly what it tells us to do to show the alpha decay of the following. So we're going to start with our parent nuclide, which in this case is thorium. So thorium, we're going to put that number, remember it goes on the top. Then you have to look at a periodic table and you'll find that TH on the periodic table, thorium, is element number 90. So we know it's going to be an alpha decay, so you can write 42He or you can write 42alpha, doesn't matter. So what numbers would go here and here that would add up to these numbers? Well, 90 minus 2 would be 88, and 232 minus 4 would be 228. And then if you look up 88 on the periodic table, 88 is what element? Well, 88 is radium, Ra. So look up this number to get the identity. Uranium, big number goes up here. Got to look up uranium on a periodic table, number 92. Alpha particle is going to be the same. Here, we'll write the alpha this time. But the same method, take this number minus this number, so that'll be 234. 92 minus 2 will be 90. 90 now, element 90 in this case, turns out to be, well, we've had that before, happens to be thorium. And notice that thorium is not the same as that one. Those are isotopes, remember, different numbers of neutrons. Notice alpha decay, but all these elements were above 83. Remember, anything above 83 on the periodic table will automatically do alpha decay. So that's alpha decay. Beta decay, take our parent nuclide. So we'll take iron, 59. That number always goes at the top. Phosphorus here, P, 32 is going to go at the top. We have to look up the element. This is 26. Phosphorus is element number 15. Now beta decay, if you'll remember, well, let's just look at one here. So we put a beta decay, and you can put the beta symbol, or you can put the electron symbol. It doesn't matter. Now, difficult math. 0, 59, that stays the same. But what number plus negative 1 equals 26? Well, that would be 27. So 27 in this case then, right next door to iron on the periodic table, will be cobalt. Now, if we look at this, let's take the top minus the bottom. That's 33. That's 33 neutrons, 26 protons. Over here, subtract, we get 32. 32 neutrons and 27 protons. So we got rid of a neutron and turned it into a proton. So in this case, beta decay, if you'll remember, too many neutrons in this case. So we switched one to a proton in the beta decay system. Same thing, we'll put the E sign this time. 0 plus the left, 15 negative. Don't do the negative 1 over here. 16 and negative 1 equal 15. And that would be your nice sulfur atom. So those are your examples of your beta decay. You can come back and watch this as many times as you want to when you're working on your homework paper. It's not going to hurt you to look at that. So what's a positron decay? Remember, positron's the opposite of beta decay. This is when you have not enough neutrons. So this time we're going to take our oxygen 14. Oxygen is element number 8. We're going to give off the positron, which is a, you can do either one. Here on the other one, we'll do 38K 19 0 positive 1 E plus. We can show it both ways. They both count. Now what plus 1 equals 8? Well, now it's 7. So here we had 6 neutrons, 8 protons. Here we have 7 and 7. So this time I got rid of a proton and turned it into a neutron. And here we'd be 38 on top. This would be 20. Oop, no, it wouldn't. Let's try 18. And 18 would be argon. So that's positron decay. That only leaves us with one more, and that's gamma. Gamma's always your easiest. I'll come back to these in just a second. Just remember on gamma, we'll just do it real quickly. Let me go off the screen here for a minute when we do those mixed examples. Gamma, if something gives off a gamma, so we say we've got something that's radioactive like iron, 2656 gives off gamma. Well, it still stays exactly the same thing because that's just pure energy. So gamma is real easy. Usually they'll tell you on the side that there's a gamma emitted with something else. So let's go look at these other examples. I'll get this thing in my way. There we go. So these have neutrons. Sometimes, now these are what are called fission reactions. What happens here is, when you guys mentioned it in your web quest, fissions, when you take an atom, you split it with some particle, and it's almost always a neutron. And you ram the neutron into it, it breaks it into parts. And when it does, it usually gives off a bunch of extra neutrons. So we're going to look at this because this is going to confuse you when you're working on your papers. So focus on that for just a minute. So tops and the bottoms have to add up. So we have 92, 0, 56. So 92 minus 56. Do that over on the side. 36 goes down here. And if we look up element 36, that's krypton. Now we have to be careful over here. 3. There's 3 of these. It could have been written that way. So there's 3 of these. That's going to make 141 plus 3. We're going to subtract that from 235. So 235 minus 144 is 1991. We'll pick this up in the next part of the video.